In the third part of Notes E from Chapter 3, we're going to focus on the magnetic property of our transition metals. You might remember that one of the four principal quantum number was the spin quantum number, denoted m sub s. This indicates that there is an actual spin that each electron is experiencing as it exists in an orbital. There is actually part of Hund's rule that described how those spinning electrons have to orient as they fill the different orbitals. Two electrons occupying the same exact orbital have to spin in opposite directions. One would be going clockwise while the other is going counterclockwise. We represent this in things called orbital diagrams by having arrows going in opposite directions. For example, maybe one arrow going up and another arrow going down, as we have two electrons sharing an orbital. Now, if this happens, the electrons with opposite spins would have no net magnetic effect because the clockwise and counterclockwise spin of these electrons would essentially cancel out. No net effect. You may also know that these completely full orbitals are more stable, so it is most common for substances to be not magnetic because they want completely full orbitals. Transition metals, on the other hand, have these giant d orbitals, which can contain large amounts of unpaired electrons. When you have these unpaired electrons, you have singly filled orbitals. So if we start getting the electrons going in the same direction in these separate orbitals, you're going to end up with magnetic properties. Using the orbital diagram can help you determine if a substance is diamagnetic or paramagnetic. So first let's describe diamagnetism. This is what happens when you have a completely full d orbital, when all of the electrons are paired. You could apply this to other orbitals as well, but since we're talking about transition metals, I do want to focus on the d orbitals. So if you have all 10 electrons in the d orbital, you have a diamagnetic substance when all of the electrons are paired. This is going to make something not magnetic. It literally would not be a magnet. It is not feeling any application of a magnetic field. All of the spinning of the electrons are directly canceled by another electron. The counterclockwise motion is canceling the clockwise motion of every single orbital in substance that is diamagnetic. Paramagnetism occurs anytime you have unpaired electrons. So we're actually going to have varying degrees of paramagnetism. Say, for example, my d orbital only had one electron in it. Now that electron would be unpaired, of course, but it's going to be weaker as a magnet compared to something that had 3 electrons in 3 singly occupied orbitals. And that would still yet be weaker than something that had 5 unpaired electrons. So this would be what we call perfectly paramagnetic, where the entire d orbital is exactly half full. And we've seen that create interesting trends in things like ionization energy, because being perfectly paramagnetic actually has a certain stability to it as well, which is going to make it harder to ionize or interrupt this perfectly paramagnetic electrical field. Not electrical field, magnetic field. So if a substance is diamagnetic, it will have actually a weak opposition to an external field, meaning it would basically be repelled from a magnetic field. If a substance is paramagnetic, it would have a strong attraction to a magnetic field. We can actually use this as a way to test to see if a substance is paramagnetic or diamagnetic. So you see that set up here. You would put the substance directly opposite something of known mass. And if there were absolutely no interaction with that magnetic field, then those two parts of the scale would be exactly even, level, as shown here. However, diamagnetism actually has a weak opposition to the magnetic field. So that substance that's diamagnetic would actually move up a bit as it's moving away from the mass. So that's going to make that substance appear a little bit lighter. On the other side, if it was a substance that's paramagnetic, we're going to feel an attraction, which is going to actually pull that substance down as if it were a magnet. And so the substance would actually appear heavier than it actually was. So diamagnetism has a very weak effect because the spin is mostly canceled out. Paramagnetism has a strong magnetic interaction that's perpendicular and proportional to the magnetic field. There are actually 3 specific atoms that have a unique type of magnetism called ferromagnetism. This is going to be not proportional but larger than the applied magnetic field. So this ferromagnetism occurs specifically in iron, cobalt, and nickel. Only those 3 atoms out of the 10 that we're looking at are going to experience this stronger response in terms of magnetism compared to the magnetic field applied in the first place. And this is possible due to the type of metallic bond where they have some long-ranged interactions, some delocalization that happens within these atoms that allows the electrons from different atoms to interact with each other. Typically, when metal atoms are around each other, they do not directly affect each other's electron configuration. That's what they mean here when they say usually their domains are randomly oriented, meaning the electrons are typically not interacting with each other and they're headed in different directions. Different clockwise and counterclockwise mean different things for the different atoms. They're not interacting with each other. In a substance that is ferromagnetic, like iron, cobalt, or nickel, if we take those metals and we apply a magnetic field to those atoms, all of the atoms then will start having the same exact rotation for clockwise and counterclockwise. So you can see this net field kind of lining up in this picture. What's really cool about these atoms is this phenomenon that once we then remove the magnetic field, those electrons will stay aligned. They will not return to the random state they were in before. And that's what makes them an especially strong magnet, for having this kind of over and above response to the application of the magnetic field. That's what makes iron, cobalt, and nickel so special, being ferromagnetic. And that's going to complete notes E3. There are some really cool videos on magnets that I usually post, and I will tag them along with this one on the YouTube playlist. And then the next video to continue our notes for notes E will be notes E4, where we will go over catalytic behavior.